Hi, welcome to my channel. This is a video on Haskell. And Haskell is a programming language that comes up quite a bit in online discussions and other areas. And when people talk about functional programming languages, it's often seen as kind of like this pinnacle of what functional programming is. And so I've seen discussions about whether you should learn it, about functional programming languages, how it's used. But it comes up often enough that I was actually motivated to kind of take a look into it and see what's changed about the language since I last looked at it, which was some time ago, back when I was working on my PhD back in the 2000s, and I wanted to see what has changed with the language since then, and what's going on with the ecosystem, and so on and so forth. And it turned out to be a very interesting exercise, and I'm going to try to share that with you. So what I'm going to start out with is just basically the journey I went down in terms of how I got it installed, what I found along the way, and then a brief example and what I learned from doing that brief example. So first of all, the setup is pretty easy. They've made a tool called GHC Up that allows you to download the needed tools, and keeps tracks of multiple versions and can pretty easily switch back and forth between them. But also shows you what's recommended, what's latest, kind of what works with what. It's pretty good. And there's probably ways of doing this via package managers, but this works actually pretty well. And I was actually quite happy to see this kind of tool. It seemed to be pretty well thought out. And what the GSC stands for in GSC Up is the Glasgow Haskell compiler. Now, this is where things got a little bit confusing to me. It seems that there's like a lot of supported versions of the compiler runtime. Right now, when I did this video, it seemed to be that there's a 9.6 branch, a 9.8 branch, a 9.10 branch, and a 9.12 branch, each of them having their own various life cycles and things. And part of what this comes down to is there's also language variants now in Haskell that people target, and so the compilers and the compiler versions each target different types of things. There's also a long-term branch that seems to be 9.2, but I can't tell if that's really the long-term branch or what's going on. So I didn't dig into it as much because I was finding conflicting information from various places about it. So that was one of the things where I found that a little bit odd. And the language variations were fairly well documented. It starts out with Haskell 2010, which is kind of the specification for the language way back then, and then GHC 2021 and GHC 2024. The interesting thing is that I think they realized that the language was never going to be implemented outside of the Glasgow Haskell compiler system, and so instead of just making it a standard where other people could implement it, they really kind of focused on taking that base of 2010 and then just really documenting what the Haskell compiler did in terms of new features and kind of group them up by year. So 2021, 2024. It's not they're being like completely informal, but they're just being a little bit more pragmatic about how the language has evolved. Now, a lot of them say that they do recommend you try to use the latest version of the language, 2024. It's recommended in the documentation, but if you go back to the compiler that they recommend, for you to use, it doesn't support 2024 features. So I found that a little bit odd. And more of the stuff kind of popped up the more I looked into it. There is some package management tooling here, but here's where they need a better story, to be perfectly honest, because there's two overlapping tools for package management and project setup. There's Cabal, and then kind of built on top of this is called a thing called Stack. And the thing about it is that what Stack seems to do is the Stack seems to say, okay, we know what you want. We want to be able to move quickly between various versions of the compiler and runtime, and we want to track packages that work with that. And so they try to make these targets, these long-term stable targets for these various types of things. And basically, that seems like a very good idea. But when I was trying to work with it and trying to get it to work, there's fundamental extensions and libraries that I wanted to use when I was using Visual Studio Code that wouldn't compile under the set of recommended compilers that they had suggested. And I was trying to figure this out for a very long time. And it seems like what they call a long-term release is really not anything long-term stable. It just happens to be a moving target in terms of the compiler. And there's a lot of things in those packages that may not be consistent. So I found the goal of Stack to be kind of being lacking to what they actually provide. And not only that, but there's still this overlap between the two tools because Stack uses Cabal to do a lot of things, but also Cabal can do some of the stuff that Stack does. Cabal can't switch the runtimes around for you, but it certainly can make a new project templates and do all the types of things that Stack does as well. And they kind of interrupt with each other. And so basically, it's one of those things where it's like, I don't know why they haven't united behind a single solution for this. Um, it seems like they should really embrace one thing and not the other. And there might be political reasons for this that I'm not aware of. That usually is what happens when things like that. That there's basically some internal schism that causes these things to fork off. It's interesting to see that Stack is kind of in this commercial Haskell site, which may have been that a business is trying to spin off to make this happen, and then people wanted to go the other way, and it seems like Cabal and Stack kind of evolve semi-independently as well. But this is just a pain. You don't need two tools here. You really do need one, and you need one to be consistent and provide all the things that you need to do. So what I ended up doing is, and that's my advice to you if you really want to look at Haskell, is to stick with Cabal until you need Stack. It's fairly simple to make a straightforward project by doing that command line there. And it's a simple project layout than Stack does, because the Stack uses a more complex notion of packages and how you organize things. And if you were to get to the point where you need it, then you can understand how to use Haskell well enough that you could then get Stack to work and do what you needed to do. I just found it for beginners to be a bit disappointing in terms of its stability and understanding what it really did. Okay. Given all this, you can set up your editor and be prepared for the new syntax and type system, because it's very new syntax. It's a really different type system and how it works. A lot of patience is going to need here, not only get the tool chain going, but also to get you into the first type of code. So that being said, I'm going to now switch into the first thing I did. And of course, I did a very trivial example, which is kind of the classic FizzBuzz thing. And so I eventually got this going. It took a little while for me to get back into the swing of things. I have looked at Haskell-like syntax before. I studied SML back when I was doing my bachelor's and a little bit of my master's. And so I'm kind of aware of that family of languages, and Haskell is in that family of languages alongside OCaml and F#. And so the syntax wasn't a complete surprise to me. But then again, it was also a surprise at how terse it had become in terms of, excuse me, in terms of how little things you have to specify versus other languages like F# and OCaml. So you can see here that this is a function. The top line is a type declaration that says this is a function that takes an int and goes to a string. And then we're using the guard syntax here to specify the various values for a function. And this kind of works very similar to how you would define basically a non-continuous function or a piecewise function in mathematics. And so this is quite where this bar guard notation comes from. And in this case, it's a fairly straight translation. Why mod is in backslashes here is really an interesting thing that I found out later on. And so I was a bit confused. I was trying to use the mod operator, the standard mod operator that other languages use, and that doesn't seem to be supported in Haskell. So I just had to do this instead. And then the last thing is that it took me a while to find that this otherwise thing, it was necessary. That's kind of the preferred keyword. They don't really like you to do a throwaway throwaway thing here. And of course you do need it, because Haskell's smart enough to look and said, it's like, if it can't prove that this is an exhaustive match, then it will say, hey, you need to have an otherwise thing here. So this is fairly straightforward once you get used to the new syntax. Again, there's no semicolons, and that can throw people off as well. Also, this equals, instead of returns. Also, just interesting little things here. So there's a lot going on here. And so I talked a lot about using this guard expression and how that's a terse way of capturing what you could always do in like if-then logic. Now, here's the thing about it is that one of the things that popped up is that I went to case statements at first, and case statements in Haskell are completely different than other languages. And the thing about it is that case statements are for pattern matching, and pattern matching is a different thing. They have some overlap with what you would look at guard expressions, but they work differently ultimately. And so again, the top line is a type declaration. The interesting thing about Haskell is that the tool will actually infer this for you, and then the editor will kind of insert it for you as a hint, and then you can just go ahead and add it to the file. And in Haskell, it's kind of considered good form to not just have the type inference for functions, but to explicitly show the function for every type in terms of documentation. And when you see how important type checking is to Haskell, you can see why that makes sense. Also, there's no syntax that says it's a function, right? It's just kind of invert from the variable after the function name. That this basically, if I have fizzbuzz I and then some stuff after it, it kind of interprets this as being a function. Also, there's a big difference here that a lot of people get caught up in. Fizzbuzz I is different from fizzbuzz with his parentheses, and what it comes down to is Haskell again is very dogmatic, I would say. And some people say rigorous, but I say dogmatic. It sees functions very much in the lambda calculus way, as a function is something that takes one value and returns a single value. And so what this means is that there's two different ways you can pass multiple values into a function. One is that you can make them partial functions, or what they call curried functions, where you can go I, j, k, with spaces in between the I, j, and k. But what that does is that specifies a function that takes in I and returns a function that takes in a j, that returns a function that takes in a k, and that ultimately returns a value. And that can be very useful because curried functions allow you to do things like partial function specialization and all sorts of interesting patterns where you can redefine new functions by only specifying a certain amount of the parameters and not all of them. But it's something that will really throw people off because, again, it's like, okay, why would you do this? Why are you doing it that way? But again, it's just because Haskell is very, very insistent that basically functions have one, take in one parameter and then return a value. Now, the thing about it is that, but Haskell also knows that basically that curry pattern has costs, and it's not what everybody wants to do. So it also supports the notion of tuples, or tuples, excuse me. Tuples are basically a selection of arbitrary types. So you can have a tuple with like 2 ints in a string, or a tuple with 2 strings in an int, or a character, and that's typed. And so each one of those are typed. And a tuple is considered a single value. And that's what's going on here. In this case, I'm declaring a function that is a tuple of an int that returns a string. And so the type signature for this is completely different from the type signature for this. And so that throws a lot of people off because, again, this is like, you can't do this in other languages for the most part. And this is what you do by default. Again, this kind of throws you off. So you have to kind of worry about this whole tuple thing and how it works with just this curried function definition. Or in this case, if you only do have a single, just, like an integer or single value that just one in that doesn't need to be a tuple, then this is how you would do it. So what I wanted to do is I was running a little bit of experiment. I was kind of curious if someone came in there and started typing in a very naive way based on some of their experience from prior languages and try to do this fizzbuzz thing. And so let's define a new version of fizzbuzz doing this. And this is what I came up with. First of all, I did eventually give back, basically they would have to figure out how this \mod things works. And so that would take them a little bit of time. But once they got that, then they would basically try to do something like this. They would note the equal thing here because that's another way of saying, oh, fizzbuzz2, the value here is it takes this thing in and does this. So this is basically this function equals this. This is how to do it. They maybe eventually figure that out. They might leave this off, and so on and so forth, but they might get this going in there. So I got it to this point, and again, when I was doing I was actually doing this in context of a loop that would take in, well, not a loop, but basically the IO was the command line would take in something, would basically prompt for a number, and then you enter the number, and then it spit back, fizz or buzz or nothing. So the interesting thing about this is I ran through this, and this is what happened. It basically gave me a single error saying there's a syntax error on the line that contains the type declaration for main, and that was it. And I went through this a couple times. At first, I thought it was a language server error, so I made sure to run the compiler, and sure enough, that's the error the compiler gave me. And I can kind of see why it's going on because I understand that what Haskell does. But the thing about it is that there's a lot of things in there where they kind of work but don't really work the way you expect. Haskell does not have an if-then statement. It doesn't exist. It has if-then-else, but you must always have the else branch. Haskell does have a return keyword. It works completely different than what we expect return to be in other programming languages. You do not use return to say what the value of a function is, the value of a function, what the value of a function returns. You don't use the return keyword at all. You use it in a completely different context. And so this is enough of the syntax that Haskell's trying to figure this out. But it's like, I'm waiting for some more stuff here before I can make this a function, and I can't quite get there. And it didn't give me a lot of meaningful feedback. And that was really interesting for me, because what it came to is like, well, if I was a less experienced programmer, where would I go from here? And when I was looking at it, it would be like, oh, you have to do a lot of research. And it turned out to be a really interesting question to ask, because what it came down to is what I realized is this. The thing with Haskell, and I think maybe a few people would argue this is a good thing, and I think there's an argument that maybe this isn't such a good thing, but Haskell requires that you really take all your notions about what programming language syntax looks like, how programming language semantics work, and set them off to the side. And you have to kind of start with this fresh slate in your mind. Like, I've never seen a programming language before. The weird thing about this is that if you were an actual beginner, it would be impossible to learn Haskell, because there's so much stuff in Haskell that requires you to know things like, oh, why you have type checking, what static type checking is, what is functional programming compared to imperative programming, right? All these things that you really have a hard time learning if you haven't programmed in other languages. And so here, your best hope of learning Haskell is to have experience with programming, but that experience with programming is fighting you when you want to try to actually learn Haskell on its own terms. And that's kind of really difficult. And that always happens with other programming languages to some extent. But I was really surprised at how much about Haskell you have to just like, oh, this is something completely different, never mind. That basically nothing works like you expect it to until you realize that you're doing something completely different. And that really raises the bar to learning about the language, I think. So why use it? There's a lot of people that like the rigor of the type system and how it leads to some very terse code that you can reason out in a mathematical way. A lot of it can be used as a specification to check other more optimized implementations against. That's what a lot of people use it to. There's some people use it as a foundation for other programs. I'll talk a little bit more about this later. But like I said, there's people that have this basically they want this very rigorous type of thing where they want to talk about correctness. And for certain domains like cryptography or security, there are some companies out there that's what they kind of specialize in, is doing this kind of stuff at a very high level, but it's very research oriented still. It's not something that you're doing day-to-day applications with. A lot of these companies are basically either funded by governments or other entities that are backing them to do basic research. There's actually a company in my town, Portland, Oregon, Gallo, which actually has a lot of Haskell programmers that they work with and stuff like that. And they do a lot of research in these areas. So the thing about that is, of course, you need to know that basically in general there's very, very little demand for Haskell in the workforce, and even in academics, it's one of those things where there's just very few academic appointments to begin with, and there's very little of them in programming language and type theory right now. So, but there's what it is. If you really need the rigor and you want to use it as a specification language, there's some really good uses for it. There's some other side projects where it's had some success, but it's really kind of hit or miss. So why learn it? And here's the thing. If you're a graduate student in CS and interested in advanced programming languages and type theory, you're going to be exposed to it. It's something that you should look at, and it'll be a great thing to have some familiarity with. If you aren't in this space, but you really, really want to learn those kind of topics and get to that level for personal reasons, fine. But please note, just note this. This will not help you find work or become a better programmer in 99.999% of the applications you're going to be looking at. So it's one of those things where if you're just interested in functional programming and want to become a little bit better at functional programming because you want to apply it to maybe make your TypeScript a little bit better, or use C# or Java better, or Kotlin, or these types of things, or maybe you want to break out and actually find another programming language to do some interesting side projects in, Haskell is not the first choice. And this will go against some people that do like the Haskell community that will insist that actually it's the best choice. And I would argue that basically it's too complicated, and the payoff that they have in rigor is too much versus what you get versus starting with something like Racket. But of course, I am biased because I am much more in the Racket side of things. But the thing about it is that arguably, Racket is targeted for people learning programming. It has been used successfully to teach computer science in multiple different universities and multiple different curricula. Haskell's never had that as a target, never been an idea. To even introduce it at an undergraduate level has never really been a thing. So it's hard to argue that basically Racket doesn't have just a massive advantage for people just coming in and wanting to learn something and they're fairly new to programming in general. Not only that, but I would say that looking at it in the sense of the ecosystem and kind of cutting down on the complexity, OCaml is more manageable, and some of the contrast would transfer to Haskell if you really want to learn that. But OCaml is a lot more easy to deal with because it's not as opinionated, but you still get used to the new syntax and some of the ideas around the type checking and type inferencing in OCaml. Also, the dark horse here is F Sharp. F Sharp is built on top of the .NET framework, also .NET Core, so it is cross-platform now. And so you can interoperate with all the .NET libraries, which it gives you a lot of really production level types of code, so you can really do a lot of interesting things. Also, F Sharp has pushed back against some of the rigor that Haskell added rather deliberately. There has been requests to do things in F Sharp that Haskell did, for example, around type classes and some of the more advanced stuff around generalized abstract data types and basically abstracting against monoids. And the inventor of the language, Dom Symes, who's still active in that community, has explicitly refused to add those features because he strongly believes that they add a ton of complexity for no real benefit. And I tend to agree with him. The amount of rigor that you get out of using more category theory than monadic, monads, yeah, no, there's very little payoff there. And it seems that the only people that really see it as a benefit are the ones that want to talk about type theory, not about making actual programs. So again, they're more interested in specification and research than they are the day-to-day of being a working programmer. And so I really admire his take on it, and a very principled take about not just putting in all these features despite some pressure to do so. For example, he basically, he allows for mutability, where Haskell doesn't. And there's some cases where he refused to add lazy extensions as well to the language. It's eager versus lazy. And that's a big thing with Haskell. Haskell also does lazy evaluation, and that often doesn't come up until you deal with things like performance or certain corner cases. But both of those, both F Sharp and OCaml, are also really good if you want to look at this kind of strictly type functional programming language in the ML domain versus Haskell. And basically, I would bite off OCaml or F Sharp before you even tried to get into Haskell as a start. Even though there's some great texts out there that try to introduce Haskell from the very beginning, again, it just becomes too difficult to do. And the payoffs really kind of diminish very rapidly. So here's the summary that's interesting. Haskell is a complex tool to gain a place in popular coding culture, but it has nothing to offer most programmers. And it's not a personal judgment. It is just kind of the reality of the programming that people do day to day. And it's just about how complex Haskell can be to approach. Not in terms of this ecosystem being fragmented, but just the sheer density and terseness of the code can be absolutely really difficult. It's one of the most, it's basically, some people really appreciate it about this, but basically it's the language that looks more like an undergraduate mathematics textbook than anything else. And I would argue that that's a disadvantage, even though I, as a PhD in computer science who likes things like advanced programming for languages and type theory, can understand those things. My interest in research has always been, well, how does that translate to making the average programmer do things better? And Haskell doesn't have a story in that regard compared to OCaml and F Sharp. And even OCaml and F Sharp, that story isn't really the most obvious one. There's some people using OCaml that in a very interesting way. One of the things I'll point out is that Jane Street has an interesting project they're working on internally that they just open sourced called OxCaml, which is basically extending the OCaml toolset to have better interoperability with Rust. So you can kind of do these trade-offs of using Rust for fast performing code, but not having to do the completely just bailing to unsafe C, which is good. I think that's really interesting, and I think that's actually might lead to some really interesting applications of that. Um, I'd also say that F sharp is kind of the language that really was, but no one ever knew that it was, because C sharp has adopted 90% of it and is almost going to basically be 95% of that with things like discriminative unions, and they already have pattern matching, all this kind of stuff. So that C sharp was very, very much influenced by F sharp. That being said, it's almost too much. So where people don't realize that if you actually start from F sharp, you're getting to a better place than if you start with C sharp. And I think that they often didn't push people into using F sharp when they needed to use F sharp versus just adding things into C sharp. That's a personal opinion. But again, same, syntax matters. It's one of those things where we know JavaScript got as popular as it did for kind of co-opting Java syntax that people kind of felt familiar with because they knew C++ and C. And going, and C sharp did the exact same thing. And F sharp, of course, being from the ML family, adopted different syntax. That being said, with Rust being more popular and Rust kind of borrowing some things from actually the ML family of languages and how they do the syntax, I think more people would be open to learning things like OCaml and F sharp. But when it comes to Haskell, it's pretty much just going to be very, very small set of people that use it. The interesting thing about it is that it's also increasingly just used as a research tool for making other specification tools. It's there's a language called Agga that is basically a version of, not necessarily a version of Haskell, but Haskell inspired, but it's one that's used for theorem proving and program specification. And that's getting a lot of traction. Of course, it itself is implemented in Haskell, which has some interesting consequences. But the thing about it is that the ultimate goal behind Agga is really just to be specifications for a language or program, and that is ultimately translated into a more performant code. There's some interest in C, obviously, as a backend, but verified C, which is its whole thing. There's a lot of interest now in having Rust as a background. There for a while there, Haskell it's still kind of a target. You can generate Haskell code, obviously, but more and more people are realizing that basically people are more interested in, when they're doing this type of stuff, they want this to translate into system programming, and that really means C, C sharp, C++, and now Rust, because Rust can do some really interesting things in terms of keeping some of the memory safety guarantees that you can be able to prove about in Agga, and move them over into a much more performant implementation. So lots of interesting things going on around that. Now, me personally, I was thinking about, well, am I going to go deeper down the Haskell road? And the answer was, as much as it'd be fun to have a series on Haskell, there's better videos out there on it already. And I'm going to spend my time, if there is interest, learning F sharp, to be perfectly honest. I'd get back in the .NET thing, and do it away and to brush up my functional programming chops on the static type system there. Just because I want to see, how that is evolved and how it's kind of reacted to what's going on in C sharp. And not only that, but I think it's a better sell now that it's cross-platform. More people actually would be really interested in it because you can set up Visual Studio Code and the plugins and all that, and it works really well. So anyway, thanks for watching. If you like this video, please do click like and also subscribe to the channel. Thanks. Bye.